therefore I think that this is completed by this software called applicability.
Okay, welcome to our third Quantum BW colloquium here on site at Stuttgart. Good to see you again. And I also want to welcome our participants in the online stream. My name is Clara Stephan, and within the team Quantum Computing at Fraunhofer IAO, I coordinate the outreach activities, including this colloquium. And yeah, last year, Quantum BW was kicked off as the state initiative for quantum activities in Baden-Württemberg to pool all these competencies and to create an overarching umbrella and brand that further strengthens these networks and makes them more visible. With this colloquium, we want to further promote the scientific exchange on quantum hardware and algorithmic topics in the field of quantum computing, to present the latest developments in this research area, and to promote the idea of co-development of quantum solutions. Yeah, we already started with the topic of quantum machine learning in May and will continue so with this focus for the next 3 sessions. And today I have the pleasure of introducing our speaker, Dr. Christa Zoufal from IBM Quantum in Zurich. Dr. Christa Zoufal is a quantum applications researcher at IBM Quantum. She received her doctoral degree from ETH Zurich on her thesis about generative quantum machine learning. Her expertise combines knowledge about quantum information theory and computational methods. As part of the Quantum Finance and Optimization Group, her current research focuses on the exploitation of quantum computing within the context of quantum machine learning and optimization problems. And today she will introduce us to the potentials and bottlenecks of state-of-the-art quantum machine learning algorithms. Yeah, with the advancement of quantum technology, researchers aim to understand if and how quantum algorithms could have advantages compared to their classical counterparts, for example, in the context of machine learning. The investigation of possible benefits of quantum compared to classical machine learning models requires thorough theoretical as well as empirical studies. And in this talk, she will firstly present an overview over potential advantages of quantum machine learning over its classical counterpart. Then she will dive deep into near-term quantum machine learning algorithms that are based on short-depth parameterized quantum circuits, which are well suited for execution on near-term quantum hardware. And these models are promising candidates for a set of near-term empirical studies targeted to understand the applicability of quantum machine learning. However, as shown by a variety of research training, these models can become challenging, especially at increasing scale. Yeah, you can post your questions in the chat, and my colleague Philipp Kunst, who is a PhD and the co-chair of this session, will collect them afterwards and also guide the discussion later on. And with that being said, I hand over to you, Christa.
Thanks a lot,
Thanks for coming around.
Thanks for the nice introduction, and also thanks a lot for having me here. This quantum machine learning is exactly what I'm working on, so I'm always looking forward to speaking about it. Sometimes it's a bit difficult. I'll try to explain the whole matter as well as possible, and I'll also try to start from some basic levels and then go into some more explicit and more recent research topics. Maybe just by a quick show of hands, how many people here in the room are actively working with quantum machine learning? Okay, great. Yeah, unfortunately I cannot do the same with the audience that is online, but great. So you will have to deal with what the audience in the room looks like now. Great, so with that being said, let's get started. As mentioned, I will speak about quantum machine learning, what are the potential advantages and what are the bottlenecks. So first up, right, on a very basic level, what is quantum machine learning? There is actually quite a bit of range in terms of interpretation, what we can understand under this field. So really on the most basic level, quantum machine learning is the combination of machine learning, where we refer to learning from patterns in relation that is given by some form of training data, and quantum computing, where we aim to solve some task better by making use of quantum mechanical resources. Also, this can really mean many things. Great. Now, this is a picture that we like to show a lot when we speak about machine learning, and it provides a nice categorization about what machine learning and quantum machine learning is and how it's being applied. So what you can see here is 4 squares. And on one axis, we have pretty much what kind of data we're looking into. So we can either study classical or quantum data. and on the other axis we have the data processing device. So whether we process the data type that we have given with some classical or some quantum resources. And what we're currently looking at is mostly in the realm of processing classical data, either with classical models or quantum models. The reason for this is that quantum data is simply difficult to get. So in practice, if you want to have quantum data, you somehow need to measure it and then have it available in some form that also allows you to process it on top of what you have. So most of the actual research that considers quantum data is now currently focusing on the purely theoretical level, and there's also some interesting insights, but we specifically at IBM are also interested in testing out our hardware, hence implementing practical experiments, and this means that we're focusing on working with classical data right now. Good, so why quantum machine learning? And let's start with the good news, right? So firstly, we do know that quantum computers can process certain very complex data structures better than a classical computer could. And what kind of data structures is this true for? Well, we know it specifically for mathematically complex structures. A very well-known example is related to Shor's algorithm, where you're trying to find the prime factor decomposition of a very large number. Another example is a discrete logarithm problem, where you're trying to identify a discrete base of your logarithm. And we have found already quite some interesting insights as to why quantum is now specifically good at solving these problems with classical data in this form, right? So all of these mathematical problems are classical. And then one more thing to mention here is that these mathematically complex problems are specifically interesting in crypto. So I will also try to build a bridge a bit later in the presentation to cryptography. Secondly, what people are interested in is exploring some processing advantages that you could make use of with a quantum computer. One example is Monte Carlo type processing, where you can achieve a quadratic speedup with quantum amplitude estimation. There's also some types of processing speedups that you can explore that are of an exponential kind. For example, HHL, which is an algorithm that solves systems of linear equations. And all of these processing advantages are, of course, also under consideration. Specifically, the exponential ones are interesting, but for those, in most cases, we do require fault-tolerant quantum computers, which unfortunately we do not have available as of today. Great. Then what are the bottlenecks? One very important bottleneck is data loading and data readout. So while we can explore some of the advantages like processing, we also need to encode our data into a quantum state to make use of those potential advantages. And this loading, as well as the readout, can actually be very costly. In fact, this can easily induce an exponential overhead, and this, of course, would diminish any possible advantage you could get with the processing itself. So what we're specifically looking for in quantum machine learning is rather small to mid-sized data that has very complex structure, or that has some properties like a very special sparsity, such that we can load and read it out efficiently. Good. Then another very important problem is flat loss landscapes. So quantum machine learning suffers from a similar problem as classical machine learning algorithms did at the very early days, namely exponentially vanishing gradients. We'll speak about them a bit later again, but at the root where the problem is you have an exponentially large search space, and if you don't have any prior information, but you do have to initialize randomly somewhere in this exponentially large space, then you will lie very, very far away from your actual solution. And because you have this exponentially large space, some concentration phenomena happen, and your loss landscape will become smooth, well, flatter and flatter, but your solution will only be in a very localized region where then you can actually train with a gradient. Good. Now, since we're at Fraunhofer, also to mention a couple of industry use cases where quantum machine learning can have a potential impact. I listed here now two fields, on the one hand finance, on the other hand chemistry. There is fraud detection, where the hope would be that a quantum neural network could achieve better classification accuracy. There's credit risk assessment and customer analysis. For customer analysis, for example, there's a quantum recommendation type algorithm, which has certain advantages compared to classical systems. And on the other hand, we also have material design, drug discovery, and rare event simulation, which are mostly related to some form of quantum simulation, which could also be supported by machine learning insights into the field. Great. Now, we've had a very broad overview. We are at very exciting times. This is a work that I like to show a lot because it has a very important message in my point of view that comes with it. So this paper presented a simulation of an Ising model, but on 127 qubits. And what was particularly interesting here is that this is now a simulation that pushes the boundaries of the best possible classical methods to do the same simulation. And actually, once this experiment came out, some interesting events happened. So the classical community felt a bit challenged, which is also good, and they went back and they started improving on their methods to again show that they can also do the same thing if they tweak certain things. So the bottom line here is now that with quantum hardware combined with error mitigation, we're currently at a point in time where we can start to actually have a challenge with the best possible classical methods. And in my point of view, that is a very critical point in quantum research. Great. There is also some more very interesting research coming up. So another field that we're specifically looking into is how to best make use of all of the resources that we have available. So eventually, right, we have very good classical computers. We have supercomputers, we have GPUs, CPUs. So we're also trying to make use of the combination such that we run whatever we can run with a classical computer, and what is hard for the classical computer, we run with the quantum computer. Now, in this work, some of my colleagues worked together with a Japanese supercomputing center, and they made use of the Fugaku supercomputer to actually run a ground state search for a system, for a chemistry system that is really not trivial. As you can see, we're here talking about, well, here we have it. We have here like 60 to 80 roughly qubits, and more than 10,000 more than 10,000 quantum gates. So really a non-trivial system, and they made use of the quantum computer then just for the sampling and the supercomputer for processing on top. And this now also opens up a new avenue, right, where you use the quantum computer for specific sampling tasks, and then you can also make use of the supercomputer resources to do all of the processing on top. And there's some very nice sampling techniques presented in this paper. So if you're also interested in quantum chemistry, I can highly recommend to have a look at this work. That's not the only paper that goes beyond the large, that goes in the range of the large qubit limit. So there is now actually quite some research that explores more than 100 qubits on the actual hardware. One paper on this list that I like a lot is the efficient long-range entanglement using dynamic circuits. What this makes use of is also a new hardware capability where you can make use of dynamic circuits. What this means is that you apply a measurement on your quantum circuit, and then you have a classical control loop in between, which, depending on your measurement outcome, can implement a certain gate again on your quantum computer. And making use of this functionality, we can now implement some gate teleportation protocols or GHC state preparations in constant depth. So that's quite cool, and this is also what this work already illustrates on actual quantum hardware. Now, 2 more IBM slides. So here you see the development roadmap. I guess many of you here in the room have seen it, but maybe the audience online has not. What you can see is that we're now here in 2024, in the time where we have the Heron processor. Actually, this processor already exists and is in use. What you can see here is that the qubit number is not that much different from the previous series of chips from the Eagle chips. But what is particularly important here is that error rates have significantly improved. So we're talking here on some levels on 10 times improvement, which is really significant. And we have a new type of electronics, which now allows for these dynamic circuits to be implemented. Here, just also really quickly, this is the innovation roadmap. So before you've also seen not only, maybe let me go back, not only the hardware, but also close integration with the software and with the application layers on top. And there's right now a lot of focus also on the software reshaping to focus on making the code run much faster and much more robust. You may have seen right now we have Qiskit 1.0, which was a big stepping stone right now, because this means that Qiskit is now on a stable version release, 1 point, and we're quite excited about it. Now, going to the innovation roadmap, right? We have said before that we're now also specifically looking at middleware and the software layers. So as you can see, so last year, 2 years ago, we had the integration of the serverless service, where you didn't always have to wait for each and every execution of quantum circuits in the queue, but you could really have some dedicated time with also a classical computer on-prem, such that you can run your algorithm within one loop, which means that due to the lack of time delay, you also have less impact of physical movement errors that naturally happen on your hardware system. So that's quite cool. Also, there is now some work on AI-enhanced transpilation going on that is now available, and currently there's a lot of work on improved resource management such that all of the experiments can run faster and faster. Now, just to flash this here real quick, if you're interested in digging a bit deeper, there's the IBM Quantum Platform with publicly accessible hardware, as well as the documentation, and down here you also find the GitHub repository for Qiskit. Just as a special note, if maybe you have worked already with Qiskit in the past years, you may have realized that we also have some algorithms and certain building blocks in there that are not here in the main Qiskit repo right now, but they're still around, right? You can just find them in the Qiskit community repository. So just as an FYI here. Great. Now, real quick, right, we touched upon it before, but just to get everybody really on the same baseline, we are specifically looking into what type of algorithms we can run with the processes that we have right now, respectively in the near term. And these near-term quantum computers are still affected by physical noise. We have to work with a limited number of qubits and also limited circuit depth. What is great is they are there. We can already try and test them. They're publicly available on the cloud, accessible to everybody. Even if in an unpaid plan, like you can go and try at the quantum computer. And we do have at least some way to work with the noise that is in the system, which is error mitigation. And there is a lot of research here going into the mathematical side, how you can fight physical errors, making use of extrapolation, making use of combinations of some twirled settings, where you can convert actually your coherent noise into statistical noise, which again means that you can reduce your error rates by making use of more samples, etc., etc. Great. What we're eventually looking for is a fault-tolerant quantum computer. Here it says noise-free. Well, this has to be taken with a certain level of caution, like it's quite likely that it will not be 100% noise-free, but we'll always have some noise in the system. And also the transition from the near-term quantum computers to the fault-tolerant ones will not just be from today to tomorrow, but we expect that we have a continuous transition from the scheme where we do error mitigation to error correction. So an integration of both levels. Great. Now, with that being said, we're focusing on near-term quantum computers, so we are specifically looking at variational quantum algorithms which enable to run computations with relatively shallow quantum circuits. The main paradigm here is that we approximate the solution with a parameterized quantum state where we run a parameterized quantum circuit on the machine. We get an expectation value, and this expectation value will inform a cost function, which again can guide parameter updating until we suffice a certain stopping criteria. So this means now we have the problem definition set up, but of course the problem definition is not what we directly run in the circuit, but there's some pre-processing involved where the quantum circuit that is given by the problem needs to be converted into a logical circuit and a fitted circuit on the actual quantum hardware, including here the compiler, which is something that, is very important to reduce the gate count and hence get sufficiently accurate results with the quantum computer. Great. Now, really quick, to give an overview of, what can you do now with a parameterized quantum circuit like this in machine learning? Here is an example where we use a parameterized quantum circuit, so a PQC, as a classifier. What you do is that you take your classical data, imagine having a vector, and you use it as parameters within your unitaries, which then prepare a state. You measure again, and this measurement informs your loss function, respectively gives you a prediction of the outcome label for the classifier. Here you have now a bit more of a detailed point of view. So what we oftentimes do is that we make use of feature maps where we fit in the classical data first, and then we apply a parameterized block, which implements the classification, where we are trying to learn the parameters here of the classification block depending on the measurement outcomes. Good. Now, why would we actually want to look into this? Well, we have found that these parameterized quantum circuits can have a higher capacity measure than classical comparable neural networks. What this means is that we can encode a larger range of information with the same number of parameters in our system. What we make use of here is specifically the effective dimension. The effective dimension is an interesting capacity measure compared to some others, like the Kolmogorov complexity or parameter counting. Kolmogorov complexity is a mathematical capacity measure which is based on the minimum description length of your learning problem, and this is actually in practice really hard to get. What you can also do as a capacity measure is count the number of parameters, because you would always expect the more parameters you have in your system, the more encoding you can do, but this is also very naive, right? Imagine you have two RY gates, one after the other, and then you just have two different parameters on there. This won't really give you an advantage in terms of what your model can represent. But the effective dimension is true size, it's data dependent, you can efficiently evaluate it, so it's really great. And we are currently looking into a benchmarking study to get a better understanding of this capacity measure on a larger range of quantum machine learning models to get some statistically significant insights in the capacities. Then a second example is our hybrid quantum generative adversarial networks. What this model does is you have a generator which generates data samples and a discriminator which takes data samples and classifies them as being either real or fake. What we can do is we can make use of PQC as a generator and a classical neural network, and by making use of this workflow we can learn a quantum state whose amplitudes represent a discretized form of a probability density function. Now that's really great. How this is being done is pretty much in a two-player game. You have a loss function for your generator, where the generator tries to, well, generate data samples that the discriminator identifies as true data. And you have the discriminator loss function, which of course tries to correctly classify whether data is real or fake. Now by an alternating training, we can, well, learn a probability density function as you've seen it before. And I will now directly hop here. So here we see one example that I do like a lot. This is a 16-qubit model. This Gaussian distribution, this target PDF that you see here, is actually something that is really hard to train already with classical state-of-the-art GANs. And we have used a relatively shallow efficient SU2 ansatz. Efficient SU2 includes RY and RZ rotations in your gate. And already with a depth 1 circuit and pairwise entanglement, we managed to train a reasonably good model, as you can see it over here. Now, just one thing that we think is missing in these types of models, you do see a type of spikiness up here, right? And what the models are still lacking is some notion of continuity, because the encoding is happening in a very discretized form, and the model right now doesn't know that qubit 1 and qubit 2 are actually next to each other, and you would expect them to be somehow continuously related. And since this notion is missing, we can see the spikiness up here. Good. On the left-hand side, you see a plot that illustrates the training for 500 training epochs. The relative entropy is a measure that tells us how close the target and the trained PDF are. You see that things push down here quite nicely, and we have some decent convergence. And then you also see some gradient plots here. So the dark orange plot is the full gradient, and then we also have here an illustration of the impact of a 1 local component and an 8 local component. Oops. Okay, and now what this means in specific, well, we'll see now in a few slides, but more importantly, locality does have a significant impact in terms of the training. And let's look at this in a bit now. So when we talk about trainability in a variational quantum algorithm, we want 3 things. Firstly, we want to have efficient access to gradients, because, well, there's other optimizers, but most optimizer need some kind of gradient access, or at least some access to the loss landscape. And this access can be, well, impaired by the shot noise that we have in the system. This can, well, irritate the gradients that we evaluate. Then we want a non-exponentially vanishing, non-exponentially flat loss landscape, such that we can do more than just a random walk in our plane. And finally, we also want to have an ansatz that is actually able to represent the optimal point. And ideally, we would also like to have a very good initialization that brings us already close to this optimal point. Where the latter is a very important question right now that we're looking at in the field, but it's very difficult to answer. So now I want to talk a bit about specifically like the second point and how we can understand and evaluate our loss landscape in an efficient way without having to run a full training. Good. So barren plateaus, for those of you who haven't heard this term before, refer to to the setting where the expectation value of the loss function gradient is 0, and the variance of the gradient vanishes exponentially with the number of qubits that are in the system. Known causes for this are either because you have a very deep ansatz, that is a TD sign, or you have a very global observable in your system. You have extensive entanglement, where you then do a partial trace at some point, which you can imagine like a maximally mixed state. And if you then do a partial trace, let's imagine we have n Bell pairs and we do a partial trace on half of the subsystem, we will only be left with a maximally mixed state. And a maximally mixed state cannot encode any information because everything is uniform. Or we can also have some noise models, some unital noise models, which will also induce some barren plateaus. However, if we have non-unital noise also in the system, then this is being broken, but then things also get very complicated. Good. So we talked already before about like a 1 local and an 8 local component in the gradient. So what does this refer to? Well, for a given ansatz in a particular initial state and a particular observable, we can define a loss function. And here now for the observable, we can always represent this as a weighted sum of Pauli operators, where the small h's are now the Pauli operators, and we have our real components on top of this. Now, this Hamiltonian can be either local, hence acting only on a few qubits. Typically, we make the statement of a local Hamiltonian up to log n terms in the Hamiltonian. We can have global terms where we have a Hamiltonian that acts on all qubits, or at least the majority of them. And we can also have mixed qubits where some of these terms here in the sum are local and some are global. And now on the right-hand side, you see the impact of what this means for the gradient of a loss function, right? So in blue, we have the local terms, and we see that here the gradient is very strong. For the global, we do see an exponential decrease in terms of the gradient strength for the number of qubits. But if we combine these two terms, then we also get a very interesting and nice behavior where only the impact of the global term gets smaller and smaller for larger qubit numbers. Good. Now, one thing that is interesting in my point of view for these barren plateaus is that there is an intrinsic difference between the barren plateaus that we have in quantum computers and in classical machine learning. So in quantum barren plateaus, the exponentially vanishing behavior comes from the number of terms, the number of qubits in the system. So pretty much of the width of our network. And in classical neural network, they came from the depth of the network. So really, the more nodes you have in there, the more multiplication you had on top, and the smaller your terms became. So just something to think about. Good. Now, the question is, good, we've seen here before, the gradient behavior can be different for different terms, but how can we evaluate this in an efficient way without having to really train the model or run exponentially expensive state tomography? So, I'll show this to you in the next couple of slides. What our results specifically change is, firstly, we have an efficient way, I'll show this, but also we relax TD sign assumptions. So existing results that give a bound on the behavior of the gradients for a variational quantum algorithm always relied on TD signs. But TD signs are, if you want to prepare them in an exact respectively approximate version only for 2D signs, this means that you need m squared respectively m in the order of gates, which is already very, very deep, right? And secondly, TD signs are only an asymptotic assumption, asymptotic statement. So the respective behavior of these signs will only be true in the asymptotic limit, which, well, you don't have in practice. especially not when you have shallow circuits with a limited number of qubits in them as well. Good. The results that are very relevant now in connection with what I'll show you is firstly here, this is a very well-known paper by Marco and friends from Los Alamos, where they showed that baryon plateaus exist for global observables. Well, they do assume local 2D signs. Then there was an extension by Uvarov and Biamonte, where they proved that if you have a cost function that is based on a weighted sum of polyterms, that each polyterm has an independent contribution to the loss function. This is important because now if you have a local and a global component, right, you will know that the local component can induce a gradient while the global will not. But we'll speak about this in more depth later. And Knapp improved on the results from Uvarov and Biamonte even more. The bounds are tighter, they're also compatible with qubits. So also really cool, I can highly recommend looking at it. But the entanglement blocks that are assumed here also need to form a 2D sign. Great. Then for what kind of problems? What kind of problems are we now looking at? Well, firstly, we make an assumption only for simplicity that we have an initial state that is a product mix state. We have an extension, so everything that I show you is true for arbitrary initial states. The formulas are just a bit more nasty. We have the Hamiltonian as we've seen it before. And now we also look at the light cone in our system. So assume you have an ansatz u theta and an Pauli term now h alpha. Then the number of qubits that these Pauli spreads out throughout your ansatz is now the light cone. Great. And the kinds of circuits that we're looking at consist of Clifford entanglement gates and product of rotation gates, where now here we have the setting that the first two layers have to be orthogonal single qubit rotations. The reason for this is just a commutation projection, and the parameters have to be independent. Again, this assumption can be lifted, but the maths gets a bit more nasty. And imagine you have two correlated parameters that are just the same, just with a minus sign, then the gradients can easily cancel each other out and therefore change our results, which are here. Good. Now, firstly, right, as a reminder, what we've mentioned before, already Uvarov and Biamonte showed this for 2D signs. We were able to show it for the circuits that I've shown you, namely that the independent polyterms in our Hamiltonian give independent contributions to the gradient of the loss function. And now here is a very important point already. Namely, we can compute the variance of our loss function, which is related to the variance of the gradient of the loss function, as an expectation value of the loss function squared for a discrete distribution D. And this discrete distribution D is what you see up here, really a distribution where your parameters are 0 or pi half. Now, what you might realize already right now is if we have a parameterized quantum circuit with Ry and Rc rotations, and those are the parameters, then we can efficiently represent them with Clifford circuits. This is great because Clifford circuits can be run on a classical computer. Now, the bounds here, right, for the variance of the loss function, which is related to the gradient, are given again as expectation values over this discrete distribution for the light cone that we discussed before, and the lower bound is also given over this discrete distribution with the light cone just with a factor of 1/4, and here we also have a measure of orthogonality, which we can compute with reasonable costs. Good. What does this mean now? If we can represent all of the values, right, all of these bounds with Clifford circuits, that means that we can really just run Clifford circuits to get the values here for the light cones, and then we can make use of Monte Carlo type, I have this here, of Monte Carlo type of estimation to get an estimate of the expectation value here. And this directly means that now here we have a very efficient way of estimating these bounds with a classical computer without having to run anything on a quantum computer. And you can also see here that they're beautifully tight. So in orange you see the actual variance of the loss function, and in blue you have the upper bound, in green you have the lower bound, and the rest of the bounds are existing ones. And yeah, you see beautiful, beautiful behavior. And I think this was, this is a global observable and a depth 1 circuit. And we have similar results here now for a log depth of the circuit and the global observable. We still see beautiful tight results, right? And we're going here up to 30 qubits, and this runs super fast on my local computer. And here, one more, we're both a log. Yeah, I'm just impressed how tight they are and how fast things went. Great. Now I think, we said we wanted 15 to 20 minutes of discussion as well, right?
You can go on.
Okay, great. Then let me just take one small excursion again into cybersecurity. So at the very beginning, we mentioned already that quantum machine learning is good at processing complex mathematical structures, right? And this got me thinking at some point, can we now make use of quantum machine learning to impact cybersecurity? And as this is a super fancy video that never works because it's too expensive, apparently, for my computer. Well, good. Just as a brief reminder in terms of quantum for cybersecurity, right? Very important, very well-known Shor's algorithm enables to efficiently solve a factoring problem, which is a security vulnerability. We can make use of quantum key distribution to share quantum keys between two parties. And now the question is, can we make use of quantum machine learning to also improve the data processing somehow, to possibly identify security threats or improve the robustness of the models, or simulate some uncertain events faster, again, possibly making use of those Monte Carlo type settings. And for classification, right, one problem that I mentioned before is this discrete logarithm problem. And for the discrete logarithm problem, we do know that there exists a special quantum kernel which can conduct this mapping. So here you see a nasty distribution between the red and the blue points, the two different classes. And by making use of a specific quantum feature map, we can actually get a nice representation where all red points are on one side and the blue points are on the other, so the classes become linearly separable. And actually, this really is a classification task that is just not possible efficiently with a classical computer. Now the question that often comes up here is, does the quantum computer enable the efficient solution of this problem because it has access to an exponentially large feature space? And the answer is no, not necessarily, right? There's also infinite dimensional classical kernels like RBF kernels, but the advantage comes from capturing the specific structure just better. And it is important to look here also at learning theory to understand if this structure also manifests itself in some other mathematical learning problems. In terms of robustness, people already started to look at this, and I wanted to highlight two results here. So firstly, in a benchmarking study, a team found that quantum neural networks can learn a set of features that was inaccessible for the neural networks that they tested, and this improved the robustness against known adversarial attacks. But this requires, of course, more benchmarking, right? And it was also found in another work that a depolarizing noise enabled to protect again against some known adversarial attacks. There is a close connection to a concept called differential privacy, if you want to look into this, but there are already some mathematical indications that there could be something here. And finally, right, simulation, this is something that we've mentioned before. There is this algorithm called quantum amplitude estimation, which can achieve a quadratic improvement. in terms of simulating some stochastic events. Here the biggest question is whether this quadratic improvement is actually enough, because error mitigation, error correction will induce a certain overhead in terms of the resources that you need. So we're looking at whether we can find some algorithms that go beyond this Grover type of speedup. But again, there is some simulation to get better accuracy with less data samples, which could be specifically interesting in finance or medicine or weather forecasts, where there's really a lack of data that you could use to train a large machine learning model. So to wrap it up, quantum machine learning, firstly, it strongly depends on the hardware progress. And we, as a message to take home, we need to develop them hand in hand, right? We need to understand the resources that we need for the algorithms and also then give this feedback to the hardware teams. Secondly, there is some potential to get better classification because we can have better capacities. We might be able to build models with improved robustness, and we may be able to get better event simulation with less data samples. But there's still many open questions, and we need to specifically look at what kind of learning problems can machine learning tackle, and how can we represent a specific problem with a good ansatz and a good initialization to avoid trainability issues. And just moving forward, this is for me also a very important message. I think right now we really need to focus on two parts. One is theory. So I hope I was able to convey to you that, I mean, at least in my point of view, crypto offers some interesting learning problems due to the mathematical construction here, where we could make some exploration with quantum machine learning. One thing that is also very interesting that I just wanted to mention is that some researchers already looked at whether quantum models are good at learning the outputs of quantum circuits. And in fact, they are not, at least for the structures that are difficult for classical systems as well. So we need to improve our understanding what are suitable learning problems and models for quantum machine learning. And this is something where we should make use of the theory. But we also need to push for empirical studies. Right now, we've observed some things already in some scattered or individual experiments, and we need to now build up a streamlined benchmarking pipeline and run experiments in a fair and reproducible comparison to extract whether certain properties really manifested themselves in the models or whether it was coincidence on the specific data sets that were looked at. And simulators and hardware continuously improved, so we also now have the ability to make some application-centric benchmarking of how these backends improve. Benchmarking, really important. We're working together with a lab in the UK, with STFC, on also doing this, and hope to release a benchmarking repository as well in the next few months. So also, if you're looking into running something practically, you can find some interesting problems there. And with that, I would like to thank you for your attention, and I'm happy to take any questions.
Right, thank you very much. As you said, now there will be some time for questions. In the chat, we didn't have any questions so far, so please feel free to address them right now. If you have any besides that in the audience, any questions so far?
Yeah, so I would have a question exactly to one of your last statements where you said that even you see that some quantum models are not really suitable to learn data generated by quantum circuits itself. So, and then in the beginning you showed, okay, the different kind of QQ, QC, CC,
Yeah.
QC. So what to your experience, or at least to your intuition, would be data structures which would benefit from quantum models in general? So I mean, this is a very open question, but I mean, if you actually see that the quantum model is not even suitable for learning an outcome of a quantum model, so what is the data structure you expect?
That's a very good point. So thanks for this question. So the work that I was referring to, right? What they're doing is that they have some shallow circuits, but they're generated via Haar random measure. So then eventually you take measurements, but what they're trying to learn is the generator, which is based on a Haar random measure, right? So this is a very difficult problem, and eventually it just turned out that because of the difficulty of the Haar random measure, whenever it was hard for the classical system to represent the generating process, it was the same for the quantum system, which is also, my point of view, somewhat related to the fact that, I mean, we will not be able to solve NP-complete problems, right, with a quantum computer either. We might achieve some kind of speed up, but we don't know. But then again, this is a very difficult problem because it's a Haar random generator. Now, we've seen some interesting work, for example, by Robert Huang, right, who showed that especially if you have access to quantum data, which you can also link in some form, that you have multiple copies that you add in one system, we can have, let's say, a quantum sensing type of speed up for specific measurements. Or one other example that I like a lot is a work by Nathan Wiebe and I think Maria Kifarova, where they do some generative learning on an energy surface. So they take a Hamiltonian family and then brute force prepare a couple of ground states, and then they make use of these ground states to feed it into a generating model, and then this generating model learns to prepare the ground states for the rest of the parameters in the Hamiltonian family, right? And this enables to have a generative model that learns an energy surface for a specific Hamiltonian family. And something of this kind seems super relevant to me. I think we have to look for the problems. They won't, unfortunately, they're not delivered to us on a silver tablet. Looking at combinations between quantum simulation, where they know that there's an angle, and machine learning is something that I think is very interesting, and I would like to look at more carefully also, because this gives us some kind of information how we should construct our answers. Right? We can make use of known techniques, tractorization, block encoding, etc., to see how we can build up already the models somewhat in a parameterized way.
I have a question. So you said that the example of learning discrete logarithm, the advantage comes from the structure and not the size of that you have access to. Then why do you think that, for example, when you use a variational algorithm, can we just find this structure that moves? So if we put a QML, why can we variationally find this structure that we would like to find in the
Can you rephrase the question? Are you specifically talking about the discrete logarithm problem?
So I think in general, because in a way, so you said that the advantage comes from having access to a specific structure. We have kind of like an intrinsic bias. But then, can we variationally find this? Why can we not do this? Because so we come across to barren plateaus, for example, in QNS, and then
you're asking a very, very good question. I think that we would be able to do the variational learning, but we need some better initialization, warm starting techniques, right? I mean, on the one hand, we do have a potential here we do know that we can represent functions with quantum computers that we cannot that easily represent with a classical computer, right? The problem is just getting there. And this getting there, I think this can only be informed by some initialization, because also the available function space, again, it's just so big. And if you don't know where to look, then you end up somewhere random. And the best you can do then eventually is just a random walk. But if we have some kind of prior information, then I believe in the representational capacities that quantum computers and even variational quantum circuits offer us.
Maybe a question for myself regarding prior information, because one of the things that I'm looking at is physics-informed neural networks and PINs. And the idea there is that you have prior knowledge, could be some PDE, some boundary conditions, which you then include in the loss function. And there's also ways to encode hard constraints in the network, at least on the classical side. But I think something similar would also be possible on the quantum networks. Is that something you have been looking at?
I mean, not in this full form. I think it's super interesting, so I'd like to hear more about it. One thing that we have looked at is so you can also describe an optimization algorithm in terms of some imaginary form of time evolution, and there's a variational form thereof. And for this variational imaginary time evolution, which again you can write as a ground state search, and the ground state search can be an optimization. And there we have looked at integrating some physical constraints into regularization components in the cost function. And that's also something that I think is very interesting, because there you have a system of linear equations, which is clear, and there you can give some boundary conditions, but I'd be interested to learn more about how you approach the problem.
Okay. So you were referring to Varkite algorithms. We've also looked at that, at least in toy problems, with respect to a potential finance use case.
Yeah.
But for the toy problem, it seemed to converge very nicely, but at the same time, the scaling there would probably be problematic.
Yeah, let's talk about this. Like, I have a complete other slide deck for this problem.
Yeah, that'd be very nice. But there were more questions over there.
So you talked about, first of all, thank you very much for the nice overview. You talked about this bottlenecks, especially data encoding, right?
Yeah.
So could you elaborate on that, how you do currently in current machine learning workflow, how do you do it, and what's the probable directions one could look into to make it less expensive?
Yeah, so that's a very good problem. Like data loading, I think, is one of the most important things that we should look at right now. So what we've done before is make use of specifically this quantum generative adversarial network to load probability distributions in an approximate form, because eventually when we train the system, right, we get this quantum circuit, and the quantum circuit represents for us a discretized form of the PDE, and this we can then process. So that's one thing. There have been a couple of papers recently that show how to load some special structures, right? So for example, when you have a sparse data point with many zeros in there, you can also make use of this to push down the complexity of the loading itself. That's one. Secondly, there is some random encodings, right? So QRAG, for example, or measurement basis encoding, where you can encode multiple bits into one qubit, but then you have a stochastic representation where, well, yeah, now it gets very technical, but you have a stochastic representation where only with a certain probability you then actually measure the right outcome, but if you repeat it, right, your average can also tell you something. I think that it would be interesting to look more at Hamiltonian encodings. So really, you plug your parameters, your data into the Hamiltonian, or you have an interesting PDE where you know the starting state is something simple, and then you can encode the partial differential equation via Schrödingerization to the Hamiltonian, and then this PDE could prepare an initial state as well, right, if you run time evolution. But again, this is costly, and for this we would need, well, more fault-tolerant quantum computers. But something along those lines I could imagine in the long term.
Thank you.
Perfect. Thank you so much, Christa and Philip, for your insights. In our next colloquium in 2 weeks, we will have Professor Zoe Holmes from École Polytechnique Fédérale de Lausanne presenting her work on the question whether provable absence of barren plateaus implies classical simulability. I'm looking forward to it, and thank you for your attention and wish you a nice afternoon.